Meet the nutrients. What are nutrients? What are the nutrients that plants require for good health, and why do plants need them? Most are common chemical elements. They fulfill one or more of three general roles. Some are structural, part of plant cells, and therefore their basic architecture. Others are metabolic, required for many of the biochemical functions within plants, from photosynthesis to reproduction. The third group are catalysts. These are substances that assist metabolic functions without being used up in the process. Sidebar: hints for success. How to remember the essential elements. Agriculture students use a phrase to help them remember the elements needed for plant growth and development. The phrase is made up of the chemical symbols for each element, which is listed below. C, H, O, P, K, N, S, Ca, Fe, Mg, B, Mn, Cuzn, Mo, Cl, NiCO, which is short for C. Hopkins Cafe, managed by mean cousins Mo and Clyde Nico. The nutrients included in this mnemonic phrase are carbon, hydrogen, oxygen, phosphorus, potassium, nitrogen, sulfur, calcium, iron, magnesium, boron, manganese, copper, zinc, molybdenum, chloride, nickel, and cobalt. Nutrients for free: carbon, hydrogen, and oxygen. Three elements that plants need, carbon, hydrogen, and oxygen, never appear on any fertilizer label, even though they can make up almost 95% of any plant. That's because plants can easily get all they need from the air and from water. Plants use lots of each, but gardeners get a free ride. You can starve a plant of oxygen if you grow it in waterlogged soil, though. See improving soggy or poorly drained soils. Major nutrients. After the freebies, the element plants need in the largest quantities are called major nutrients. These are the elements most likely to limit plant growth in gardens. That's why they're the ones that you're most apt to recognize from fertilizer labels. The major nutrients are nitrogen, phosphorus, potassium, calcium, magnesium, and sulfur. They're sometimes called macronutrients. Three of these major nutrients are most familiar to gardeners because they're the ones that appear in standard fertilizers: nitrogen, phosphorus, and potassium, or NPK. Most soils that are gardened or farmed intensively need periodic replies of all three. Often, but not always, they must be applied every growing season, which is why they're included in most standard fertilizers. Three other major nutrients, calcium, magnesium, and sulfur, already exist at adequate levels in some soils. They may not need to be applied at all, or at least not as often as the previous three. Gardeners with acidic soils who apply lime every few years know the importance of calcium and sometimes magnesium to the soil chemistry. They may not need to add sulfur, though. Gardeners with alkaline soils usually face the opposite situation. They may be used to adding sulfur periodically to adjust soil chemistry, countering the effects of too much calcium and/or magnesium. Sidebar: did you know how small is a trace? To give you an idea of the difference between major and trace nutrients, consider the needs of corn. During a growing season, an acre of corn can easily withdraw 150 pounds of nitrogen from the soil. But those same plants might withdraw only a half an ounce of a trace element like boron from an acre. That means a corn needs over 4,500 times as much nitrogen as boron in its diet. Micronutrients. Micronutrients are also called trace elements because only a very small amount, a trace of each, is required for healthy growth. They include iron, boron, manganese, copper, zinc, and molybdenum. The importance of these nutrients has become more obvious with increased use of synthetic fertilizers. When farmers and gardeners had to depend on manure for major nutrients, they didn't have to worry about micronutrients. The current generation of synthetic fertilizers is so purified that few, if any, micronutrients remain in them. As a result, deficiency symptoms, once thought to be diseases, are now more common. Crops grown on soils lacking in these nutrients may fail to supply human dietary needs, even if the plant don't appear to suffer. You may never have to worry about micronutrients if you routinely add compost or manure, or if you use fish emulsion and or liquid seaweed as fertilizer from time to time. Micronutrients should never be added unless soils are known to be deficient, and then only in recommended amounts. The difference between helpful and harmful amounts is incredibly small. Also, deficiencies of micronutrients are often irregular, occurring only in some areas of a garden. Pockets of poor drainage, where soil pH differs from the surroundings, or where the soil has washed away, are likely spots for small-scale deficiencies. Chlorine, nickel, and cobalt. Like carbon, oxygen, and hydrogen, chlorine and nickel don't need to be applied to soils. Researchers have proved that plants can't grow without them, but gardeners don't need to worry about them. Cobalt is required by some plants and many microorganisms, including nitrogen-fixing bacteria. The amount of cobalt needed is too small to even measure, so again, you don't need to worry about it. Beneficial but not essential. The element silicon doesn't qualify as essential because many plants grow well without it, but some plants benefit from added silicon. So think of it as a beneficial rather than essential nutrient. Corn contains high levels of silicon, which helps make corn stalks stiff. As you might expect, corn is one of the plants that benefits from added silicon. Silicon also appears to increase disease resistance. Sand, silica, is naturally rich in silicon. Green sand, a special type of sand mined from the ocean that's green in color, is best for adding silicon to soil. It's also a good source of potassium. Granite dust is another good source. Both of these are excellent slow-release sources of essential micronutrients. Identifying deficiencies. A deficiency of an essential nutrient harms plants by slowing or stopping particular functions. In order to grow, plants have to produce new cells. If a nutrient required for cell division is lacking, the plant can't make enough new cells, so growth slows dramatically, or even stops. Sidebar. Disease or deficiency. Several plant diseases besides chlorosis, iron deficiency, are now known to be caused by nutrient deficiency. Blossom end rot affects tomatoes, melons, and bell peppers. It's caused by too little calcium, which often appears when plants are stressed by lack of water. Wither tip is merely a lack of copper. Gray speck on oats, speckled yellows on sugar beets, and marsh spot on peas are all caused by insufficient manganese. Hollow heart of cauliflower, beets, and turnips is caused by too little boron. Corky areas in apples are also from boron deficiency. Yellow spot, which affects citrus fruits, is merely a lack of molybdenum. Whiptail, which is recognized by weirdly distorted long leaves of cabbage and related plants, is also caused by molybdenum deficiency. Looking for signs. By the time nutrient deficiencies become visible, some damage has already been done. A soil test can detect deficiencies before they can cause damage. However, since soil changes over time, and since you can't test the soil in every part of your garden, it helps to know how to recognize common nutrient deficiencies. These are easiest to recognize when they're severe and hardest to recognize when more than one is present at the same time. Consulting the chart on page 204 to 205 will help match your plant's symptoms with a probable cause. Try to figure out the cause of any nutrient imbalance before you attempt to correct it. If the deficiency is caused by a physical soil problem, such as the sidebar mentions, or interference from too much of another nutrient, which will show up in your soil test, you won't fix anything by dumping on fertilizer. Once you identify a specific deficiency, you can turn to Chapter 6 for information about the best sources of that particular nutrient. Is it really a deficiency? Before you assume you're missing nutrients, rule out other causes. Addressing such causes can alleviate deficiency symptoms with no added fertilizer. Using a foliar spray of liquid seaweed or fish emulsion combination can keep plants growing until long-term improvements occur. Environmental problems. Drought, heat, and cold, or growing a variety or a plant not suited to your climate or soil, causes poor yields more often than does a lack of fertilizer. Low temperatures, as in early spring, Overwatering and underwatering can make nutrients temporarily unavailable. Pests or diseases. Some pests and plant diseases can cause many of the same symptoms as nutrient deficiencies. If only one type of plant is doing poorly, look for a critter as the culprit. Root knot nematodes can impair plants' ability to absorb existing nutrients. Aphids and spider mites cause yellowed leaves. Viral diseases can cause mottled, yellow, or deformed leaves. Physical soil problems. A nutrient may be present but locked up by poor aeration or poor drainage. Alkaline or very acidic soil is the most common cause of locking up available nutrients. To maximize nutrient availability, try to maintain that soil pH of 6.3 to 6.8. Are the symptoms on the upper leaves? Some nutrients stay put. They can't move within the plant because they're built into the cell structure. Sulfur, calcium, iron, manganese, boron, and copper are needed to make healthy new leaves, but plants can't borrow them from elsewhere if there's not enough. As a result, deficiency symptoms of these structural elements will show up first on young, upper, or outer leaves. Are the symptoms on the lower leaves? Some nutrients get around. They're really shuttled around within the plant. Nitrogen, phosphorus, potassium, magnesium, molybdenum, and zinc. That means if plants aren't getting enough, they can move these to young growing tissue where they're needed most. As a result, deficiency symptoms of these mobile elements show up first on older, lower leaves and eventually spreading to the rest of the plant. Soil acidity. Acidity of soil is one of the most important factors behind fertility. It affects nearly all soil properties, from chemistry to biological activity to structure. Correcting soil acidity or alkalinity may improve your garden more dramatically than any other soil building effort. Acidity is caused by the amount of hydrogen ions present in the soil. When you test your soil's acidity or alkalinity, what you're really measuring is the concentration of hydrogen ions. Did you know? Sidebar. Sweet and sour soils. Acidic soils are sometimes called sour soils because substances that are acidic often taste sour. Vinegar is a common acid that tastes sour. Its pH is between 3 and 4. Don't try tasting strong acids such as sulfuric acid, though. They'll burn a hole through your tongue. Farmers used to test their soil by tasting, and they could tell when it was too acidic if it tasted sour. Alkaline soils used to be called sweet soils since they're the opposite of acidic soils. They don't taste sweet, though. Any old-time farmer who learned to recognize alkaline soils by tasting will tell you that they're actually bitter. Acidity affects how nutrients dissolve. Acidity controls nutrient supply by controlling how well nutrients dissolve. In very acidic and alkaline soils, most nutrients dissolve very slowly or not at all. They may form insoluble mineral compounds, locking up nutrients so the plants can't use them. If your soil's too acidic or alkaline for nutrients to dissolve easily, you can waste a lot of money on fertilizer. Plants will be able to reach very little of what you apply. That's why it's important to test and correct the pH of your soil before you add fertilizers. The best way to test pH, see the illustration on the facing page. To correct pH, see Chapter 7. By correcting extreme acidity or alkalinity, you can bring more nutrients within the plant's reach without adding any fertilizer. This is especially true for nitrogen, phosphorus, potassium, sulfur, molybdenum, and boron. The scale for measuring pH shown in the illustration runs from 0 to 14. The pH scale above shows acidity or alkalinity of some common substances. Neutral soil has a pH of 7. Lower numbers mean increased acidity. Higher number, increased alkalinity. The pH at which each nutrient is most available will vary slightly. The ideal range to maximize nutrient availability and therefore plant health is between 6.3 to 6.8. If soil contains ample organic matter, many plants will tolerate a pH between 5.5 to 8. On the acid scale, lemon and lime run 1.3 to 2.4. Grapefruit 3 to 3.3. Sphagum peat moss or swamp peat or sphagum moss between 3 and 4. 2.5 and 3.5, I'm sorry. Average garden soils, as mentioned, fall between 6.3 to 6.8, but can vary between 5 and 8. Pure water, 7, and it's right in the middle between the two. Arid desert soils can range between 9 and 11 in alkalinity. Ammonia, 10.6 to 11.6, and a strong lye solution can be as much as 14, and strongly alkaline. Testing soil acidity. Litmus paper is an inexpensive way to test your soil's pH. It comes in either short strips or a roll of 1/4 inch wide paper saturated with special dyes. You touch a short piece to the garden soil mixed with a little distilled water. The paper will change color. You compare this color to the chart that comes with the litmus paper to find out the pH value for your soil. It's accurate within about a half a pH unit. A pH meter is more expensive but more accurate option. It's a simpler, portable version of the equipment used by soil laboratories to test pH. Both use electrodes to measure hydrogen ion activities. Similar meters are available for testing soil salt levels. The next illustration is the soil pH in the United States, showing the acidic soil on the East Coast and some along the far west coast, with most of the middle prone to being alkaline. Acidic soils are common where rainfall is abundant. Rain washes out chemicals that counteract acidity. Gardeners east of the Mississippi River and in the Pacific Northwest generally have acidic soils and need to raise soil pH. Alkaline soils are common in areas with little rainfall. Gardeners in the southwestern United States and much of the West generally have alkaline soils and need to lower pH.